Welcome to this lecture on principles of ecology. Today, we are going to explore a fascinating topic, predator defense mechanisms. Imagine playing a high-stakes game of hide-and-seek in a dense forest, where losing means you become someone else's dinner. How do animals survive? We will uncover the brilliant survival tricks nature has developed to give the underdog a fighting chance against bigger, faster, or stronger hunters. Let us dive in. Now that we have introduced the topic, let us think about what this means intuitively. Why do these mechanisms matter? In the wild, nature is essentially a high-stakes game of hide and seek. If a prey animal just stands out in the open, it will be caught immediately by the seekers, which are the predators. To survive this dangerous game, prey species need special tricks up their sleeve. This could be wearing camouflage, running incredibly fast, or carrying a heavy shield. These survival tricks are exactly what ecologists call predator defense mechanisms. They are absolutely crucial because they give the underdog a fighting chance against hunters that are often much bigger, faster, or stronger. Building on that intuition, let us look at the formal definition. Predator defense mechanisms are specific evolutionary adaptations that prey species develop over generations. Their primary purpose is to reduce the risk of being captured and consumed. We can categorize these adaptations into different types. First, we have morphological defenses, which are physical barriers. Think of the hard shell of a turtle or the sharp quills of a porcupine. Then we have chemical defenses. These involve producing toxins, poisons, or foul-tasting secretions. A classic example is the bright but deadly poison dart frog, which warns predators to stay away. Beyond physical and chemical traits, we must also consider how animals act. This brings us to behavioral defenses, which encompass specific actions animals take to survive. Instead of relying on armor or poison, these prey might flee rapidly, play dead, or form massive herds to confuse attackers. Over millions of years, a process called natural selection heavily favors prey individuals that possess these advantageous traits. Because these individuals survive longer, they are able to pass these life-saving genes down to their offspring, ensuring the continuation of the species. Understanding these different types of defenses leads us to ask why they are so vital to the entire ecosystem. Without these vital defense mechanisms, predators would quickly consume all available prey, leading to the rapid extinction of the prey species. Shortly after wiping out their food source, the predators themselves would starve and die out, causing the entire ecosystem to collapse completely. These defenses drive an ongoing evolutionary arms race, where prey constantly evolve better shields and predators simultaneously evolve better weapons. In real-world applications, understanding these mechanisms helps conservationists protect endangered species and helps agricultural scientists develop natural pest control strategies without relying on harmful chemical pesticides. Now that we understand the ecological importance, let us look at how we can quantify this. While defense mechanisms are physical or behavioral traits, ecologists can mathematically model their impact on an ecosystem by modifying standard predation equations. The formula is C equals A0 times 1 minus D times N times P. Let us break down every symbol. C represents the total number of prey consumed by predators in a given time period. The symbol A0 stands for the baseline attack rate, which is how often a predator successfully catches a prey when there are absolutely no defenses. The variable D represents the defense effectiveness coefficient, a number between 0 and 1, indicating how well the prey's defense works. Finally, N is the total population density of the prey, and P is the total population density of the predators. When the defense effectiveness D increases, the term 1 minus D becomes smaller, meaning fewer prey will be consumed. Conversely, if the predator population P increases, consumption goes up unless the prey increases their defense. This formula we just saw leads us to an important practical application. Let us see this with a concrete example. Imagine a forest ecosystem with a beetle population density of 1,000 individuals per hectare, hunted by birds with a density of 50 individuals per hectare. The baseline attack rate is 0.01 per day. The beetles have a chemical defense that is 60% effective, so D equals 0.60. We want to calculate how many beetles are consumed per day. We plug our values into the modified predation formula. The term 1 minus 0.60 gives us 0.40, representing the 40% of attacks that are still successful. Multiplying the populations gives 50,000 potential encounters. Multiplying the baseline rate by 0.40 gives a new effective attack rate of 0.004. Finally, we find that exactly 200 beetles are consumed each day. Without the defense, 500 would be eaten. So this chemical defense saves 300 beetles daily. Now that we have used this formula to find consumption, let us look at a more critical survival scenario, where we must work backward to find the required defense level. Imagine a herd of 500 gazelles, hunted by 20 cheetahs. The baseline attack rate is 0.05 per week. To avoid extinction, the gazelles must keep the total consumed, C, strictly at or below 100 individuals per week. We need to find the minimum defense effectiveness, D, they must maintain. We start by writing down our modified predation formula. Then, we substitute all of our specific savanna ecosystem values into the equation. The left side represents the absolute maximum number of gazelles that can be safely lost. On the right side, we have the baseline attack rate multiplied by the unknown defense factor and the population densities. This sets up our algebraic derivation. Continuing from our initial setup, our next logical step is to simplify the right side of the equation. By multiplying the 500 gazelles by the 20 cheetahs, we find there are 10,000 potential predator-prey encounters every week. We then multiply this massive number of encounters by the baseline attack rate of 0.05. This simplifies the equation significantly, giving us 500 times 1 minus D. The number 500 represents the total number of gazelles that would be eaten if their defense effectiveness was exactly 0. Since they can only afford to lose 100 individuals, we divide both sides by 500. This gives us 0.20 on the left side, meaning the cheetahs can only be allowed to succeed in 20% of their baseline hunting capacity. So we have simplified the equation down to its core components. This brings us to the final step of our derivation. To find the actual defense effectiveness, we simply rearrange the equation to solve for D by moving it to the left side. Subtracting 0.20 from 1 gives us a final result of 0.80. This means the gazelles must maintain a defense effectiveness of 80%. Their combined defensive strategies, such as early warning calls and rapid sprinting, must successfully thwart 80% of all cheetah attacks. If their defense effectiveness drops even slightly below this critical threshold, the cheetahs will consume more than 100 gazelles per week, and the population will shrink rapidly toward local extinction. Now that we have proven the mathematics behind survival, let us visualize this relationship. On screen, You are looking at a graph that plots defense effectiveness on the horizontal axis against prey consumed on the vertical axis. Notice the thick, downward sloping curve. As we move to the right, meaning the prey's defense effectiveness increases, the curve drops sharply, showing that far fewer prey are consumed. Above the graph, we see a perfect physical interpretation of this. On the left, a predator easily consumes an undefended fish, representing a high attack rate. On the right, the prey has deployed a morphological defense, puffing up with sharp spikes. This physical barrier directly reduces the attack rate, pushing the ecosystem down that survival curve. We have covered a lot of ground today, so let us summarize the most important ideas. First, predator defense mechanisms are vital evolutionary tools that keep prey populations from being completely wiped out. Second, whether through thick physical armor, toxic chemical sprays, or clever evasive behaviors, these adaptations fundamentally reduce the predator's successful attack rate. Third, by mathematically modeling these defenses using our modified consumption formula, ecologists can accurately predict population dynamics and understand the delicate balance of life and death. You have now mastered the core principles of predator defenses. Ultimately, this constant, high-stakes struggle for survival is exactly what shapes the incredible diversity and complexity of life we see on Earth today.